and giving a talk in CMSA, and I'm glad to be here and catching up with old friends. Okay, at various times I spoke about these results, partial results, but I don't think I ever spoke about the results when we completed all of them together. So it's good to come back and give talk with the whole results. So I'm going to be talking about the famous black hole stability problem, which says that there's a certain solution of the Einstein equations. Let's see what's happening. Yes, so there's a certain solution for the Einstein equations called the Kerr family of black holes. And this stability problem says that if you perturb the black holes a little bit, the perturbed solutions go back to the Kerr family. It doesn't have to be exactly the original Kerr space-time, but it's a stability within the Kerr family. To admit someone. Okay. Many of you may have heard about that, but in any case, for completion, I'll discuss all of the background and what are its main issues. And then I'll be talking about the Maxwell perturbations of the Kerr space-time. So I said when we talk about the stability problem, we perturb the Kerr black hole space-times slightly within the class of the Einstein equations, but an interesting and actually a popular, it used to be quite popular intermediate problem is the question of Maxwell perturbations, because there are quite a few similarities in the between the Einstein perturbations and the Maxwell perturbations. So I'll tap onto that and discuss that problem at length, because that will reduce some of the technicalities that we usually encounter when the long mathematical formulas that we usually encounter when we talk about the perturbations of the Einstein in the Einstein equations. So, but finally, I'll also talk a little bit about the Einstein perturbations of Kerr black hole spacetime. So much of the discussion, many of the topics here will be specific for Axially symmetric perturbations. That's where this work will be focused on. And some of these results in principle can be extended in general, but the actual results concerning the positivity are restricted only for the Axially symmetric spacetimes. In particular, Axially symmetric perturbations of Kerr black hole spacetimes for non-vanishing angular momentum. Okay, so these results, I'm going to focus mainly on the Kerr black hole spacetimes, but these results can also be extended for the Kerr-Newman black hole spacetime, which is a more general black hole spacetime within the class of the Einstein-Maxwell perturbations. So that's a much more elaborate and even more technical result. And that work is with my postdoc mentor at Yale, Vincent Moncrief. Okay, so speaking of the Kerr-Newman spacetime, let me show you the Kerr-Newman spacetime. Maybe most of you have seen that. I mean, it's really not important to look at the structure of the Kerr-Newman spacetime for this talk, but just to show you some overall picture of the Kerr-Newman spacetime. That's how it looks like, the solution of the Einstein-Maxwell equations. It's also called an electrovacuum solution of the Einstein-Maxwell equations. One thing that I want you to observe is that in these coordinates, in the Boyle-Lindquist coordinates, it has non-vanishing shift, and that has some implications for the discussion that will come later. So it's a solution of the Einstein-Maxwell equations, of course. Another observation is that it admits it's a so-called stationary solution. It admits a dt kilometer field. I hesitate to call that a time-lag kilometer field because it's not always time-lag, and that's the source of the main problem for us as far as the stability problem is concerned. So it has a dt kilometer field, and it's also Axially symmetric. It has d phi kilometer field, and it represents massive rotating charged black hole spacetimes. Okay, and it's not just for the stability problem that the Kerr-Newman black hole spacetime is important. In fact, arguably, it's one of the most important. It's the most important family. In fact, the Kerr black hole family is arguably the most important black hole family because of the connection with the so-called black hole uniqueness hypothesis or uniqueness theorems, which says that depending on certain regularity conditions on the horizon of the black hole and asymptotic conditions, it's expected to be the unique solution of the Einstein equations within those conditions of asymptotically flat and regularity conditions on the horizon. So it's due to that reason the Kerr spacetimes are also frequently studied. And another property of that is that you can actually, in the Boyer-Lindquist coordinates, you can actually find out where the domain of outer communications is and where is the event horizon. It's, if you look at the quantity delta inside that metric, and if you find the roots of that, the higher root is where the event horizon lies, and outside that is the domain of outer communications of the Kerr-Newman black hole spacetime. In fact, I forgot to mention that. Let me mention that. So there, it's the most general spacetime that we're going to talk today. But if you plug in Q equal to 0 there, you'll get the Kerr black hole spacetime, of course. And if you plug in A and Q equal to 0, you'll get the Schwarzschild black hole spacetime. Okay. So similar analysis also works just as well for the Kerr black hole spacetimes as well. But what is important for us is that in the domain of outer communication, there's a region, which is a very peculiar and interesting region. It causes some problems for us in the black hole stability problem, is the so-called ergo region. It's given by the quantity there. The problem with that is that the dt Killing vector field is not always time-like, as I was saying earlier. In fact, it becomes space-like inside the ergo region that creates trouble for us as far as the black hole stability problem is concerned. And it results many peculiar processes called the Penrose process. And for the wave version of that, the so-called super radiance and so on and so forth. So that's the main. In fact, I'll focus mainly on the problem caused by that in this talk. So to paraphrase the Kerr black hole stability problem, we have a solution of the Einstein equations. Everybody knows that for us, interested in geometry, it's a manifold. And has a metric on it, and it's a solution of the Einstein equations. In particular, it's a solution of Einstein equations with vacuum. I mean, with the source equal to 0. And you have a solution, and it's a Einstein equations. If you choose any suitable gauge, it's a system of partial differential equations. So the solution of a system of partial differential equations, and for us mathematicians, the stability means if you perturb the solutions a little bit within the class of the equations for which it is a solution to, it's expected that the perturbations are such that they eventually converge to another family of the Kerr family of black hole spacetime. So the perturbations should also preserve that it's a perturbation is also a black hole. It has to be a black hole spacetime, and it's a Kerr family of black hole spacetimes. Okay, so that's very elaborate and difficult problems, and some spectacular progress has been made in recent times. And I'll discuss one version of the one result that we obtained in that direction. Okay, as I said, it's a very important problem, so it's pertinent to discuss some background results, some important results in the directions. I'm going to talk briefly, gloss through some of the famous results in that direction. The first results in the so-called black hole stability problem came for the case of the Schwarzschild black hole spacetime. As I said, Schwarzschild black holes are those which are non-rotating, so the parameter A is equal to 0 in the metric that I showed you before, and it's a static solution of the Einstein equations. In fact, they're maybe everybody has heard that it's a unique spherical symmetric solution and so on and so forth. So there are many classic results in that direction. The thing with the Schwarzschild spacetime is that dt Killing vector field doesn't have the same problem as it does for the Kerr spacetime. In particular, this Schwarzschild space-time doesn't have ergo region, but it's not a highly non-trivial problem. There are many interesting results in that direction. The first results in that direction were due to Regge-Wheeler and Zerilli, who considered the perturbations of the Schwarzschild space-time, and they decomposed the perturbation of the Schwarzschild in terms of mode on a mode-by-mode decomposition, and for even and odd, was so-called tensor harmonics, spherical harmonics. And they considered even and odd parity perturbations. I mean, Regge-Wheeler and Zerilli separately, and they constructed a certain wave equation-looking equation that was satisfied by those perturbations. And a Hamiltonian version of all of that, Hamiltonian and also gauge invariant version of that, was constructed by Moncrief, which will play a very important role in this talk. Is due to Moncrief. So following that, there are many important results in recent times. In fact, nowadays, the most updated result is that even non-linear, not just linear, but non-linear perturbations of Schwarzschild has been significantly addressed by the works of Daframos, Rodniansky, Taylor, and I'll talk a little bit more about that later, and Kahneman, Scheftel, and so on. All the various works of them, they address that problem. But before that, there were also works on the linear scalar wave equation of propagating on Schwarzschild, and some early results involving the scalar wave perturbation of Schwarzschild involved the so-called Moravec estimates, and so on and so forth. I'll speak a little bit about that as we go along. And later on, there was also some discussion on the Maxwell perturbations of Schwarzschild, and so on and so forth. Okay, so the bottom line is that in all of those methods, in fact, in general, I think most of you will agree that by far, from the point of view of partial differential equations, the most potent, the most powerful technique that we have is to prove decay of any field, any wave propagating hyperbolic any equation, is using the energy, is to control the behavior of fields at large times, depending on a certain conserved quantity in time. Okay, so the famous Kahneman-Sobolev estimates, and so on and so forth. Many results, including results based on micro-local analysis and harmonic analysis, and so on and so forth, are also based on positive definite and conserved energy, including even the Lyapunov methods, and so on and so forth. All of them are strongly based on having a positive definite energy as a tool to start with. Okay, so I think most of you will agree with that. So in that context, the first result that showed that there is a positive definite energy for the perturbations of Schwarzschild is due to Moncrief. As I said before, it came a little bit after the Regge-Wheeler-Zerilli results, and he showed that there exists a positive definite Hamiltonian energy for gravitational perturbations of the Schwarzschild spacetime using the tensor harmonics decomposition. And recently, so this is about the names that I mentioned is about the linear perturbations. Recently, there are some results that are based on Euler-Lagrange approach of the Schwarzschild perturbations, gravitational perturbations. And among one of them, Holzhegel was able to recover a version of a positive definite energy for the perturbations of Schwarzschild. That was obtained by Moncrief, and later on also by Karthik and Wald. And perturbations of Schwarzschild using metric coefficients was obtained by Hung, Keller, and Wong. But that is for the metric coefficient, perturbation of the metric coefficient, as far as I understand. So moving on to Kerr, as I said, so for the Schwarzschild spacetime, we do not have this problem of the ergo region. So even there, positivity is by far not trivial. As you can see, it was a substantial amount of work. It was not trivial by any means. But here we have the added complication of the ergo region, that even the linear wave equation. I want you to focus on the second point there. So even for the linear wave equation, let's forget about gravitational perturbations or Maxwell perturbation. Let's start with the linear scalar wave equation propagating on the Kerr black hole space-time without any symmetry. You can clearly see that the canonical energy that you construct for that has an indefinite sign. So even, I mean, that quantity that creates trouble drops out if you consider actually symmetric linear wave equation. But for any general wave equation, that doesn't apply, and there's a problem already for the linear wave equation. So that's a problem for us because, as I said, we need a positive definite. I mean, it will be great to have a positive definite energy, positive and conserved energy for the perturbations, but there's a problem here. That problem has been overcome by various very impressive techniques over the course of several years. And one standard technique is due to, I think, these early works in early 2000s, where one constructs a certain energy using a blend of the dt and d Killing vector field. As I said, so the dt Killing vector field itself doesn't give a positive definite energy, so you somehow get some positivity out of the d phi by considering a blend of that. But that has a problem in the sense that, I mean, you need to cut off the chi there is some kind of a cutoff function to make the energy a finite quantity. But the problem there is that that energy is not conserved. So to obtain uniform boundedness even of that energy, it takes some really fancy, very difficult techniques to show that that energy can be controlled in time. In fact, as far as I understand, a very standard and famous technique is the use of a Moravec's estimate, which is like a space-time integral estimate to control these energies in time, which are like in 3+1 dimension sense, like the boundary terms, right? So that's very difficult work, and there are many impressive works as I showed there. Since we're on the topic of listing the past works, let me briefly go through some results there. So early results were on the linear wave equation, initially for small angular momentum, and the later results were due to rapidly rotating. And so one point that is perhaps relevant to mention here is that as the angular momentum increases, the effects of the ergo region become stronger and stronger. It becomes even more tricky to prove the boundedness in time. But nevertheless, there are some very interesting results that, interesting and impressive results that showed that the linear wave equation can be understood even in rapidly rotating but sub-extremal black holes. Okay, and then there are some results for the Maxwell equations on the Kerr black hole space-time, and most recently there's some really very impressive progress on the gravitational perturbations. In other words, the Einstein perturbations of Kerr black hole space-times by various groups. Anderson, Begdal, Blue and Ma, and Hefner, Hinch, and Wassi, Kleinman, Shiftel had a series of results that proved that even the nonlinear stability of Kerr black hole space-times for small angular momentum, and also another very elaborate and very impressive work by Daframos, Holzigel, Rodniansky, and Taylor, who proved nonlinear stability of Schwarzschild. So all of those results apply for small angular momentum, okay, because of this issue of ergo region that I mentioned. Okay, so now I'm going to talk about our results and how our results sort of fit into this whole scheme of results. What we were able to show is that if you consider, let me give you the result already, and then explain how we did it. the result that we showed is that if you integrate, so as I said, for the linear wave equation, right? For actually symmetric linear wave equation, the problem of ergo region doesn't arise. But as you go to higher spin fields, let's say, for example, for the Maxwell fields, the issue again comes up. So the issue somehow doesn't go away. So the term that causes the trouble still remains, and still poses the same problem as before. But what we were able to show is that even though the energy density, right? So the energy, the sort of loosely speaking, the integrand within the integral of the energy could well be negative across various regions of the domain of outer communications of the Kerr black hole space-times. If you integrate it out, right, the total integrated energy can still, there exists a total integrated energy that is positive definite. So that's our main result for both Maxwell perturbations and Einstein perturbations of the Kerr black hole space-times. So that is significantly different from many of these really impressive results that I just spoke about, because the method is considerably different. For that, so how do we do that? Let me show that. So our results are based on the Hamiltonian approach of the Einstein equations. In particular, let me use the Maxwell perturbations as a test case, or as an important intermediate test case for the Einstein equations. So we start with the original Hamiltonian of the Maxwell equation, just as you have the Hamiltonian for somebody wants admission. Just as the Einstein equations have a variational formulation, right? Just as the Einstein equations have variational formulation, you can also have a Hamiltonian variational formulation of the Maxwell equations. You can find that it's not discussed everywhere somehow for whatever reason, but you can go back to the original work of MTW where they discuss that. In fact, they introduce the Maxwell equations as a way of introducing the Hamiltonian formulation of the Einstein equations. So we start from there, and if we have axial symmetry, there's a very interesting structure that allows you to make some very non-trivial but interesting computations that were done in the literature in the past for the black hole uniqueness problems. And somehow there's a connection between these two for this particular special case of the problem, which allows us to construct a positive definite energy through a series of transformations. So I'll go through that now. So we have this Hamiltonian variational principle here, right? So that's the result, but let me go through the details. So in the axially symmetric setting, you can go back to the orbit space. In other words, the quotient space. You can quotient out the d phi, symmetry. Go back, so go to the orbit space. What that does is that allows you to construct the so-called twist potentials, which are defined as follows: the lambda and eta quantities, that's the reason why we're able to do that has got strong connection with the Maxwell constraints. If you observe carefully there. So what you can do is that if you introduce these variables, and if you look at the original the original Maxwell variational principle, and reduce the variational principle in terms of these twist potential variables, you will clearly see a certain Hamiltonian structure emerging for these dimensionally reduced variables, the twist potential variables. So in other words, you can also write down Hamiltonian variational principle of these twist potential variables. You may think, okay, what's the point of that? Okay, sure, until this point, nothing much happens. If you do that, you'll get this alternative Hamiltonian energy, H alt here. As I said, so if you look at the phi components of the E and B fields of the Maxwell tensor, you'll get the conjugate momenta of these twist potentials, okay? So you get an entire Hamiltonian structure there. And if you write that down in terms of if you write down the ADM Hamiltonian variational principle in terms of these dimensionally reduced twist potential variables, you will get this H alt, right? And you can clearly see that the problem doesn't get resolved just by doing that. You can see the final term there. It has an ambiguous sign. It has indefinite signs. It has the same problem as before. But something interesting happens there in the sense, okay, so these are also, you can also construct the Hamiltonian field equations, Hamiltonian evolution equations in terms of those variables, and I listed that and so on. So I'll come back to that later. So there's something very interesting happens. So you have this Hamiltonian energy, right, which has an indefinite sign, as we just discussed. But in those variables, something interesting happens. You see, those terms have got something that have strong connection with a certain identity, wherein you can transform away those terms with ambiguous sign into terms which have a positive definite form plus divergence terms, right? And the divergence terms, depending on the regularity conditions on the horizon axis and infinity, you can choose that in such a way that they vanish, right? In particular, if you choose, for example, compactly supported perturbations, then of course those divergence terms vanish, especially in this gauge invariant problem of Maxwell perturbations of Kerr spacetimes. So so that's the key. So somehow, and this identity doesn't just come out of the blue, it's due to Carter, as I'll discuss later. But we generalize that if you, for the case where it also works for n, where n is the lapse of the dimensionally reduced Kerr spacetime. So if you do that, this transformation gives a positive definite energy. So it may seem like it's somehow one is tampering with the Hamiltonian structure. So let me go back to the this slide here. As I was saying, where is that? This final slide here. So as I said, you have this original energy that is corresponding to the dt, flow of the dt kilometer field, right? But you can also construct a positive definite energy by considering a blend of the d phi kilometer field and construct a positive energy. So what I'm trying to get at is that you can construct a positive definite energy, but the key is that it has to be conserved. It has to be Hamiltonian. So if we do this transformation, we need to demonstrate that this transformation doesn't tamper with the Hamiltonian structure of the previous energy. I hope that's clear. So, but it turns out, very interestingly, that the Hamiltonian structure remains intact. So this energy is positive, but also conserved. It also is a Hamiltonian for the original phase space variables. So that's the key part here. So we have a conserved Hamiltonian energy, which is also positive definite. Okay, so that's the key observation, and we need to establish that. And establishing the equivalent results for the Einstein perturbations is a little bit tricky and technical, but I'll discuss a little bit towards the end of this lecture. Okay, so that's the key. And you can also, without having to resort to all of this Hamiltonian terminology, you can also establish a nice clean conservation law of what I was saying earlier by constructing a space-time divergence-free vector field. Okay, so that's it's pretty clear that that corresponds to a conservation law for which the time-like component is this positive regularized Hamiltonian H reg here. Okay. So that's the overall scheme of the main results. The main result is somehow written in this scheme here, and it also works just as well for the Einstein equations. But each of these steps are significantly more tricky for the gravitational perturbations because of gauge issues that come up. I'll discuss a little bit more about that towards the end of the lecture. Okay, so so yeah, so these results can also be extended for the Einstein equations of Kerr spacetime, Einstein perturbations, actually symmetric Einstein perturbations of Kerr black hole spacetimes. In fact, you can also extend that for Einstein-Maxwell perturbations of Kerr-Newman spacetimes, and that is what I stated here. Okay, and the energy for the Einstein perturbations I just showed there for the pure vacuum Einstein perturbations of Kerr spacetimes, Kerr black hole spacetimes. You may wonder about this term, but that really is a gauge related term, because for as everybody knows, in the context of the Einstein equations, energy always has to be defined in terms of hypersurface. And now I'm talking about the bulk energy. Okay, so there's this notion of energy on a so-called surface integral approach on a two surface, the so-called ADM energy, quasi-local energy, and so on and so forth, that Professor Yao and others have worked on. So, but I'm talking about the bulk Hamiltonian energy here, because the main reason for constructing this energy is to study the evolution in time. And for that purpose, and as I said, to use this energy for PD techniques. So for that, the sort of the bulk version is more convenient. So I'm talking about that. Okay. So for the concept of for this framework, for the concept of energy, we always need three-dimensional hypersurface, and for that we need to do this 3+1 splitting. For that we always need to choose a gauge, and this quantity can be gauged away. In particular, if you choose maximal hypersurfaces, that quantity entirely vanishes. Okay, so that's not a troublesome term. Therefore, the whole energy is positive. If you do not want to choose maximal, you can always use some version of the Young's equation and so on, so that Professor Yao and Sean and others have mastered over decades. But in any case, so that's not a troublesome term, in case you're wondering about that. Okay. What I did not mention is that behind the scenes, what is going on is that for axially symmetric spacetimes, what we're doing is that we're performing the so-called dimensional reduction of the vacuum Einstein equations, and for the Einstein-Maxwell case, the Einstein-Maxwell equations, into a structure called the Einstein wave map structure. And if we do the Hamiltonian version of that dimensional reduction, we'll realize that candidate for the Hamiltonian energy is given by some techniques based on the so-called linearization stability methods. In particular, if you do the dimensional reduction, the lapse of that is the kernel of the adjoint of the dimensionally reduced constraint map. And that's the key for constructing the Hamiltonian energy for us. But even if doing so is not enough, as I mentioned earlier, because we need this transformation that transforms away the ambiguous sign into post-definite form plus divergence terms. Okay, so these divergence terms for the Einstein equations cause serious trouble that we actually had to struggle for like 3 years before completing these results. Yeah, that's why in my previous talks about this topic, I didn't speak about that, but that's I'm glad I'm talking about that. So, and those terms, I'm glad to, I mean, the papers are already out, but I'm glad to announce that they all vanish and do not create any trouble. Okay, so this idea of using this Carter's identity from black hole uniqueness theorems is due to Dane and D'Austria, and in their work they constructed a positive definite energy for perturbations of extremal Kerr black holes, actually symmetric perturbations of extremal Kerr black holes, using the so-called Brill mass. Okay, so that's in some sense back to you know, one of the original results for positivity of energy from 1959 or something like that. But they developed that for cases which are not hypersurface, not restricted to hypersurface orthogonal and so on. So, okay, so it's their idea that they use this black hole uniqueness theory, and they extended that to the black hole stability problem, for the extremal black hole stability problem. But what we observed is that if you look at the original Carter's identity, that doesn't just work for the original choice of a certain quantity that he uses as rho, and you can construct the same identity for any general n. In fact, that general n happens to be a harmonic function, and that as a result is the kernel of the adjoint of the dimension reduced constraint map. So that's the observation that allows us to extend their results to the sub-extremal case, and also for the Einstein-Maxwell case. Okay, so I have a few comments about how we prove that this transformation doesn't tamper with the conservation law, and how the energy is still strictly conserved even after we do these series of transformations involving these variables. And that's what I'll talk in the next few minutes. Just a quick question. How much time do you have? Is it like 50 minutes and questions, or?
Oh, yeah, like you still got like 20 minutes, I guess. Yeah, you still have 20 minutes.
I still have 20 minutes. Okay, fine. So I think that's okay then. As I already mentioned earlier, we need to prove that the energy is strictly conserved in time for that energy to be useful, because one can always construct a positive definite energy on a fixed slice and not worry about the evolution, because that's always possible, but that will not be useful from the point of view of from the stability problem, which is based on evolution of the data from the initial data, right? So that's an interesting problem, as I already alluded to earlier. It is considerably tricky to prove that for gravitational perturbations, because of the fact that it's not a gauge invariant problem. For the Maxwell case, the advantage is that it's a gauge invariant problem. So, for example, right, if you start with compactly supported initial data, the future development is on the future of the initial, where the data, where the region where the data is initially supported in that compact region, right? But for the gravitational problem, it is not necessary, right, that the data is stays within that compact region, because, of course, Einstein equations have the finite propagation, but you need to choose the right gauge for that, and this is not the right gauge. The gauge that we use to construct the positive definite energy, which gives us the positive definite energy, the Einstein wave map gauge, is doesn't allow finite propagation speed, right? So that causes significant trouble, because even if you start with compactly supported initial data, it's not necessary that the data stays compactly supported in time. In fact, you pick up some boundary terms, and they cause serious trouble. I have a couple of comments about the boundary terms as well, right? So that's not just the only problem. You see, in the axially symmetric space-time, there is an issue with the regularity at the axis, where one has to be careful always. But not just that. The choice of the gauge here, the Weil-Papa-Petro gauge, which we use and which gives the Einstein wave map system, has a structure that, if you observe carefully, e to the 2 gamma here is the norm of the d phi kilomectre field, right? I mean, it's the length of the d phi kilomectre field. And that blows up at infinity as well, right? But there's a form where it blows up at the axis as well, but the axis also goes to infinity. And also the axis intersects the horizon at a right angle. So in other words, from the elliptic PDE point of view, we have a region where you have a sharp corner, but the angle is like 90 degrees, right? So, or pi over 2, right? So it's not a, a region with small angle that we can somehow estimate and so on. So that creates serious issues. So the boundary terms, first of all, could have geometrical meaning, and secondly, they also are, the boundary is such that it has all of these regularity issues. It's due to that reason, somehow it may seem like the positivity is great, but proving that the energy is strictly conserved in time has all of these really serious issues. And we struggled with that for several years, and luckily we were able to resolve that, and I'll briefly discuss how we did that. So the way we overcome all of these issues is that we pose the initial value problem using the harmonic gauge first, right? So we have the Kerr space-time, and we have perturbations of the Kerr space-time in the harmonic gauge, and let's say we have a compactly supported perturbation, and we evolve the perturbations in the harmonic gauge, and we transform the perturbations into the Weil-Palmer-Petru gauge. In other words, we'll get the Einstein wave map system after that transformation. And then we prove that these boundary terms all decay at infinity and at the horizon, and that they do not cause any trouble at the corner of the axis and the horizon. Okay, so that's the overall idea of that. The reason for using the harmonic gauge is that it ensures that the initial data, the propagation of the regularity of the initial data is also causal, right? And then we can just focus on the boundary terms. And in the proof, it becomes particularly convenient that much of the elliptic theory can be reduced into a system of some sort of a Poisson type equation, where, for example, the gauge transformation Killing vector field admits certain really nice elliptic properties, so that you can directly prove, establish the decay rates of those fields at infinity and at the horizon. Okay, so once we did the transformation, we go one by one to all of these boundary terms, and first the original phase space which form the boundary terms by looking at the wave map variable first, and then the gauge dependent quantities later, and so on and so forth. Okay, so so that's the overall idea of that. It's quite technical. I do not want to bother you with too much technicalities, but if you have any questions, I'll be happy to answer. Okay, so so let me wrap up in the next few minutes. That's the overall idea. The point now is that since we have a positive, definite, and conserved energy, we can go back to the energy methods that I initially alluded to and prove the decay of fields to start with, to prove uniform boundedness of the fields in time, and later on also decay of the fields in time. So that sort of restores this line of using energy methods to prove the stability problem back again for this special case. That's the main idea and the theme of these works. And as I said, actually, the first bullet point there is a topic that I wanted to talk about significantly in this talk, but I was not able to complete the work and in the time. So as I said, the total integrated Hamiltonian energy is a gauge invariant quantity, but local fields that constitute that energy, in particular these phase space variables like wave map variables and the other metric perturbation variables, are locally gauge dependent quantities, right? So if you're able to, for example, show uniform boundedness and decay of those fields, that's good progress, but that's not enough because, well, because they're gauge dependent variables. For that, there are some very classic results by Tucholsky, who used a certain combination of the Weyl tensor in projection of the Weyl tensor in the null tetrad, and it showed that certain extreme, so-called extreme components of these Weyl tensors are gauge invariant variables, and they decouple. So it will be convenient to establish, it's in fact mathematically important to establish the uniform boundedness or even decay of the fields in terms of these gauge invariant Tokolsky variables. But the problem with the Tokolsky equation is that, in fact, that's the decoupling that was established by Tokolsky is considered to be a miraculous result. In fact, it's due to one of the miraculous properties of the Kerr spacetime. But the issue there is that the Tokolsky equation doesn't admit a straightforward variational formulation, right? So constructing an energy for that becomes incredibly difficult because there's no variational formulation, there's no Hamiltonian and so on and so forth for that, except for S equal to 1 for spin equal to 0, which is of course the linear wave equation. Then it's possible, of course. But for higher spin fields like mod S equal to 1 and mod S equal to 2, the Tokolsky equation doesn't admit a variational formulation. But for this special case, using our Hamiltonian energy, we can construct an energy for the Tokolsky variables as well, if you're able to find a transformation between our twist potential variables and the Tokolsky variables. And that's a partial result of that was obtained by me back in 2019. But for the decoupled Tokolsky variables, also one can reconstruct that. For the Maxwell case, it's particularly simpler as always. But for the Einstein equations also, it is possible. So one can revive the energy methods also for the Tokolsky variables. And one doesn't have to. So Chandrasekhar transforms the Tokolsky equation for small angular momentum, as far as I understand, to Regge-Wheeler form. But with this energy for this special case, we do not need to use the Chandrasekhar transformation to the Regge-Wheeler equation and directly deal with the Tokolsky variable. So that's the plan for that. But maybe sometime I'll come back and talk about that, because I was not able to. In fact, I requested Puskar to give me a later date so that I can complete that work. But due to my teaching duties, I was not able to do that. But I'll maybe talk about that on a different occasion. So you can use that to prove uniform boundedness and decay of the fields. And these results can also be extended for the de Sitter spacetimes as well, where the perturbation region is a compact region outside the event horizon of the Kerr de Sitter black hole. And for that also, you can consider a related system called a generalized Einstein wave map system, where the essential structure of the Einstein wave map system remains, but we have some added term that can be dealt with in a nice manner for this one. So that's a work in progress. I did that work for the Maxwell equations back in 2018, but you can do the same for the Einstein Maxwell perturbations as well. That's a work in progress. And of course, the eventual aim of all of these results is to study the nonlinear problem. In that, again, there are these regularity issues, of course, and there's a way to tackle the, at least establish a certain propagation of regularity result using certain wave equation satisfied by the curvature, the so-called Penrose equation, and study that for this special case. And finally, I alluded to this issue earlier, that all of this result is based on a so-called bulk Hamiltonian approach, right? So it's a three-dimensional integral of the Hamiltonian, that is the Hamiltonian that we're considering. But there's a school of thought that says that the originally goes back to Regge and Teitelbaum, I think, who established a certain surface integral approach of the Einstein equations, and an interesting version of that is to consider a surface integral form of these results, or even for the Schwarzschild perturbations, and look at whether you can get a positive definite surface integral within some inner boundary, or if you consider the horizon as the inner boundary, some intermediate surface between the inner boundary horizon bifurcation to sphere and the sphere to infinity as a surface under consideration, and study the positivity properties there. So I think I briefly spoke about that in one of your member seminars a long time ago, but that's an interesting extension that one can consider for this problem. Okay, so with that, I'll end. Thank you very much for your attention.
Okay, thanks, Dr. Gudapati. Thanks for your good talk. Now is the question time. Any question or remarks? Any question is welcome. Dr. Gudapati, I have a quick question.
Okay.
Have you considered about the perturbation under a scalar Einstein equation?
No, no. So this
scalar.
Sorry.
The case of scalar field will be very different.
Could be. I don't know. So the point, this whole structure is dependent on the dimensional reduction to the Einstein wave map system, right? Reduction from 3 + 1 to 2 + 1 Einstein wave map system. Whenever that's possible. In fact, one result, I didn't mention that, but one result that's an extension of this one, in fact, that can be easily extended, at least the part where you make these transformations, is the dimensional reduction from higher dimensional spacetimes, because they preserve the Einstein wave map system. So as long as you have the Einstein wave map system, you can do that, but I don't know if that works for the scalar field.
Okay, thank you.
Okay.
Any other question? Okay, if there is no question, I will stop recording.
Okay, thank you very much.